Hello and welcome. Today you will learn how the integrated composite engineering solution from Dassault System can accelerate all aspects of the design, validation, and production of complex composite parts and structures. Let's start by looking at the problems designers face when trying to design complex composite parts with traditional mechanical CAD solutions that are not optimized for the composites design process. At the preliminary design phase, there's no easy way to define and manage the huge amounts of geometrical data and repetitive design tasks required to define composite parts. And there's no integration to FEA analysis tools in order to quickly validate part pre-dimensioning early in the design process. At the detailed design phase, traditional mechanical CAD tools cannot cope with defining the fiber type, direction, and stacking of laminates, plies, cut pieces, and cores, making it very difficult to get an accurate 3D representation of these parts for use in downstream digital mock-ups of the complete product. There's also no integration with the highly specialized structural analysis tools in order to ensure structural integrity and performance of the design component for complex load cases such as fatigue, impact, and delamination. There's also no easy way to output all of the composites design data for early manufacturing analysis, resulting in no ability to predict manufacturing issues early in the design process, or to integrate with highly specialized composite manufacturing processes such as hand layup or automated tape laying and fiber placement systems, resulting in manufacturing delays and increased costs caused by trial and error on the shop floor. These fragmented tools and processes lead to slow innovation through the lack of cross-discipline integration and collaboration, increased costs and delays through late discovery of errors, and manufacturing inefficiencies caused by the inability to validate the manufacturing process early, resulting in trial and error on the shop floor and program delays. Such an approach no longer meets today's increasingly demanded requirements for composites development. The integrated composite engineering solution from Dassault System addresses these business pains with an integrated suite of capabilities, specifically developed to meet the needs of composite designers, analysts, and manufacturers. The solution starts with the design of the composite components in the context of the complete assembly. CATIA supports a number of design approaches that fully defines and manages all the composite data used to drive the detailed analysis and manufacturing preparation of the part. The tight integration between the design and advanced finite element analysis context allows the rapid optimization of the design to avoid under or over engineering of the part. Similarly, the tight integration between the design, analysis, and the manufacturing context enables the early verification and optimization of the composite part to ensure it can be built reliably, consistently, and in an affordable way that will meet all initial design requirements. This integrated solution supports many composite manufacturing processes such as wet and dry hand layup of fabrics or unidirectional tapes. The majority of liquid composite molding techniques, including resin transfer and vacuum-assisted resin transfer molding, and most of the automated placement processes, including tape laying, fiber placement, braiding, and forming. We'll come back to explain how we support these different processes shortly, but first, let's start by explaining how we address the preliminary and the detailed design of composite parts. For preliminary design, we have partnered with Collier Research Corporation to integrate their hypersizer solution within CATIA for efficient optimization of the size, weight, and manufacturability of composite parts. This integrated solution can reduce structural weight by more than 20% by optimizing the cross-sections, dimensions, materials, and stacking sequences of composite components for all load cases and failure modes. A number of different design approaches are supported for preliminary design, such as solid slicing, zone or grid, with the choice of approach varying depending on the characteristics of the composite part or the panel being designed. The grid-based approach shown here is mainly used for designing stiffened panels, where the boundaries are based on a grid that is defined and driven by interstructural components such as fuselage frames or longitudinal stringers. Optimum product design can be reached early in the design process by leveraging the already created zone and ply definitions, the integrated finite element analysis solver, and composite-specific post-processing capabilities. The intuitive and easy-to-use analysis capabilities helps bring structural analysis out of the expert domain and into the core of the enterprise-wide design process by allowing engineers to quickly validate design choices directly within the design environment. For early estimation of composite parts cost and trade studies, we have partnered with Galarath to integrate their SEER Ply cost estimator technology directly within CATIA. Accurate part cost trade studies can be performed directly within CATIA to quickly generate detailed cost estimates for material and tooling, as well as the labor costs for setup, manufacturing, inspection, and rework. At the detailed design phase, there are many automated capabilities available to accelerate the overall design process, such as analyzing where we need to insert angle cut corners and then automate the generation of these cuts to multiple individual plies in just a few interactions, or quickly define, analyze, and edit the different local drop-off strategies that are to be applied to the individual plies within a section, with a number of predefined drop-off patterns available for selection. Powerful tools are also available to create cutouts such as this window opening, and then automatically ensure that all ply trimming is correctly handled. The business benefit from these process-specific design capabilities is significant. Initial design time can be reduced by up to 40%, with design modification time being reduced by up to 60%. Change orders can also be decreased by over 90% by eliminating the late discovery of design errors during the downstream analysis and manufacturing. Now let's look at how we analyze, optimize, and validate our designs for structural integrity and thermal performance. As the design progresses, it's possible to use the more advanced capabilities provided by Abacus to perform detailed, nonlinear analysis of situations such as impact, delamination, fracture, and fatigue analysis of composite parts and structures. Let's have a look at some examples of these advanced analysis capabilities in action, starting with impact analysis. The Abacus nonlinear solver uses a finite element mesh that can be quickly created from the composite properties defined during the initial design phase. This full associativity between design and analysis enables the automatic sharing of composite properties such as material, ply thickness, direction, and boundaries to eliminate data transfer errors and accelerate the overall process. In this simulation of a bird strike to the leading edge of a composite wing structure, the result of the analysis shows the deformation and delamination of the individual composite layers caused by the impact. Similarly, comprehensive modeling, simulation, and visualization capabilities are provided for analysis of fracture and delamination modes of composite structures with support for both moving and stationary cracks. These simulation capabilities deliver a highly accurate prediction of how composite parts will behave in real life. This comparison between a virtual simulation and a physical test of a real component demonstrates the accuracy of the analysis process, increasing confidence in virtual simulations and minimizing the need for physical testing, saving both time and costs. We have partnered with Convergent Manufacturing Technologies to integrate their Compro simulation software with our Abacus finite element analysis solver in order to analyze and compensate for manufacturing process-induced deformations. By importing the geometry definition of a part directly from CATIA, in this case a wing structure, we can simulate the deformation induced by the composite curing process. When we then analyze the difference between the required final shape and the computed deformed shape, and then use global morphing to counter-deform the individual mold line to compensate for this deformation, and finalize the mold phase, reduce the mold tryout phase from weeks to days. These advanced analysis and simulation capabilities drive significant business benefits. They provide and support multiple composite simulation methodologies to deliver highly accurate results that save costs by minimizing physical testing. Automated design optimization and trade study exploration allows engineers to quickly converge on optimum composite solutions, saving significant time and money. And finally, the ability to deliver innovative products quicker by demonstrating regulatory compliance through virtual simulation and validation. Now we need to produce the shop floor manufacturing information for the different manufacturing processes that we support, starting with hand layup. We start by using interactive dynamic draping to visualize how material will behave depending on the seed point selected for the draping of plies and sequences. This early analysis allows the designer to experience the ply layup process and eliminate potential manufacturing problems before they're found on the shop floor. Similarly, interactive producibility analysis capabilities simulate how the fibers of a ply group, or sequence will behave depending on the actual manufacturing strategy used. The producibility table allows the efficient simulation of these production strategies and provides summary results to help identify potential manufacturing issues early in the design process. In this example, a ply sequence that forms part of a composite airframe structure is being reviewed. By defining the seed point and fiber direction, we can visualize how the sequence will be formed from 200 mm wide material, with the producibility analysis automatically flattening the sequence in order to perform the analysis against the flattened profile. This flattened profile can then be extracted and used to define the splicing of cut parts, and then automatically generating the flattened profile for each cut piece needed to make up the final ply sequence. When it comes to dress up of the parts to be cut, we can automate the generation of rounded corners to all plies at once, or quickly define darts to be cut to ensure smooth draping over complex shapes. For hand layup, shop floor documentation such as detailed ply books can be quickly and accurately generated either as a series of 2D drawings or as a 2D layout for 3D design. These ply books can be automatically generated and also updated after a part design change, saving drawing production time and increases accuracy. In turn, this high-quality shop floor documentation makes it possible to save 25% or more on the layup of composite parts. Our unique Composites laser projection solution defines and exports laser projection files for use on systems such as those from Vertec, Assembly Guidance, and LPT. These laser projection systems assist ply placement during the hand layup by projecting the shape of the ply to be laid on the mold to ensure accurate and fast positioning of fiber components to drive a consistent, high-quality production process while avoiding trial and error. For automated fiber placement systems, we have partnered with Coriolis Software to integrate their CAT fiber product directly within CATIA and Delmia. This integrated solution provides a complete environment of the design and offline programming of 6-axis automated fiber placement machines to produce a large variety of size and shape composite parts. To accelerate the design of 3D braided composite parts, we have a unique solution that provides advanced fiber braiding simulation. It allows designers to define and visualize fiber paths on complex surfaces and optimize machine parameters to achieve the desired fiber orientations and mandrel generation to guarantee correct fiber volume and minimize mass. Finally, we have a fully integrated solution for 3D composites forming that provide an extremely efficient formed part design workflow that starts by defining material characteristics and part contour profiles through to advanced analysis and simulation of the actual forming process. The powerful simulation capabilities make it fast and easy to understand the impact of the forming process on each individual ply and to optimize the part design early in the development process. To minimize material waste, we have partnered with JetCam to leverage their high-performance nesting solution that has been shown to reduce fiber material wastage by up to 10%, saving companies hundreds of thousands of dollars a year. All of these manufacturing preparation capabilities drive significant benefits. The early incorporation of the manufacturing constraints helps to cut manufacturing design time by up to 50%. Reliable producibility analysis, flat patterns generation, and nesting significantly reduces material waste to reduce material costs by 15 to 20%. The virtual simulation and optimization of manufacturing procedures can reduce layup time by 70% while avoiding the high costs associated with shop floor trial and error or scrapping faulty parts. This integrated composite engineering solution is implemented in over 500 companies in multiple industries. We have worked and continue to work in close cooperation with many of our leading aerospace users, including Airbus and Boeing, to evolve the specifications of the solutions and address industry needs. Some users include Terrafugia, who has chosen this solution to optimize their composite layups in order to maximize strength and durability while minimizing weight for the innovative flying vehicle. They have managed to accelerate the design of their proof of concept vehicles, reduce the vehicle weight significantly, and cut development times through the complete integration of composite design and analysis processes. ACT Aerospace have reduced the time required for detailed composite design and prototyping by 90%, reduced material usage by more than 15%, and have cut the lead time required to produce first prototypes from a month or two to 3 to 5 days, depending on the complexity of the part. GKN Aerospace also chose our integrated composite engineering solution to eliminate data translation challenges and the time-consuming process of troubleshooting composite layups on the shop floor. They can now accurately simulate layup in the design environment by integrating every aspect of design and fabrication to reduce manufacturing engineering time by approximately 50%. So to summarize, the industry-proven integrated composites engineering solution from Dassault System is used by over 500 companies to design, validate, and produce their complex composite products. The solution delivers a real competitive advantage through integrated design, analysis, and manufacturing excellence. It accelerates the entire composites development process to get new products to market faster at lower cost with improved quality.